Major depressive disorder, or MDD, is one of the most prevalent disabling illnesses affecting between 6 and 21% of people at some point in their lives. MDD is often treated with antidepressants. There are many antidepressants available, with different mechanisms of action. Unfortunately, each one is only effective in 30 to 40% of patients, since MDD is such a heterogeneous disease and individual antidepressant response is so unpredictable. This means that the current standard of care for prescribing antidepressants involves some amount of trial and error. The clinician selects an antidepressant they think will work on the patient, perhaps based on some heuristics or whichever drug has the least objectionable side effects to the patient. The patient takes this antidepressant for 8 to 12 weeks and goes back to the clinician. At the end of this period, if their improvement is satisfactory, they can keep taking that particular antidepressant. Otherwise, the clinician has to modify the treatment, selecting another drug to try. As you can imagine, this process is quite tedious and lengthy. Even after a year or more of this trial and error, 30 to 40% of patients still haven't had satisfactory improvement. In the meantime, they continue to suffer. They're unable to be productive at work or school, their social functioning might be affected, and they could even have suicidal ideation. So we definitely need a better way to assign antidepressants to each patient accurately and quickly. In this project, we created a predictive tool to do just that. We looked at one particular antidepressant, bupropion, which works by increasing levels of dopamine in the brain. Dopamine is used in neural circuitry that process reward and punishment and is believed to be deficient in MDD. We created a deep learning model to predict an individual's outcome to taking bupropion and to predict whether or not they'll achieve remission based on imaging measures of brain activation before they start treatment. To develop this model, we used data from the EMBARK study, which is a large multi-site clinical trial studying antidepressant response. From this data, we obtained 37 subjects who received 8 weeks of treatment with bupropion. To measure clinical severity before and after treatment, the Hamilton Rating Scale for Depression, or HAM-D, was administered. A higher score on the HAM-D indicates greater severity. To measure their brain activation patterns, these subjects underwent fMRI using a reward processing task designed to simulate the areas of the brain that respond to reward and punishment. Specifically, it involves 24 trials of a number guessing game that looks like this. In each trial, a number from 1 to 9 is randomly selected. The subject doesn't get to see the number, but they are instructed to guess whether the number is less than 5 or greater than 5. It's entirely a game of chance, so they have a 50% chance of being correct in each trial. After entering their response, the subject is then told about the possible outcome of the trial. There are 2 types of trials. Possible win trials, where the subject wins $1 for guessing correctly and gets nothing for being wrong, or possible loss trials, where the subject loses 50 cents for being wrong and loses nothing for being correct. By having these 2 types of trials, we can measure the subject's brain activation response to both reward stimuli and punishment stimuli. Next, the actual number is revealed, and the subject is informed whether they won money, lost money, or won or lost nothing, depending on the trial type. After obtaining these fMRI scans, we did some pre-processing to correct for head motion, remove the skull, co-register the images to a template, and smooth the voxels. We then used SPM to do a task-based GLM analysis and generate contrast maps, which are spatial maps that indicate which brain regions activate or deactivate in response to specific conditions during the task. We computed a contrast map for the anticipation condition, which is right before the actual number is revealed in the trial, and for a reward expectation condition, which is a difference between anticipation in possible win and possible loss trials. Once we had these contrast maps, we reduced them to a set of regional measurements. We used the Kretek method to generate a study-specific brain parcellation, which we believe more closely segments the functional networks in depressed brains than an off-the-shelf, healthy brain atlas. Using our parcellation, we divided the brain up into regions of interest and computed the mean contrast map value within each region of interest. This gave us a vector of features for each subject to input into our predictive model. Now that we have these features, we could start training and tuning our deep learning model. We used a simple dense feed-forward neural network, where the inputs were the contrast map features for the 2 conditions, anticipation and reward expectation, and the output was the change in HAM-D score after treatment with bupropion. To optimize the hyperparameters of our neural network, we conducted a large random search, which is an efficient and unbiased way to search the hyperparameter space for a high-performing configuration. We tested 200 different randomly sampled hyperparameter configurations in combination with 3 different granularities of our study-specific parcellation, as well as an off-the-shelf brain parcellation. That's a total of 4 different parcellations that we tested. And that gives us a total of 800 distinct model configurations. To validate, we use nested K-folds with 3 inner and 3 outer folds. It turns out our neural architecture search worked quite well. The 800 model configurations we tested showed a wide range of performance, which is what we want because it shows that we searched a sufficiently large expanse of the hyperparameter space and found both relatively high-performing and low-performing models. We can compare the hyperparameter distributions of the top quartile of the configurations and the bottom quartile of configurations to see what values of hyperparameters work the best. We can see that, for example, the top quartile favored our study-specific parcellation with 100 rows, while the off-the-shelf Schaefer parcellation was used more often by the poorer performing configurations. We also see that the top performing configurations tended to use about 350 to 400 neurons in the first hidden layer. Let's look at how well the best optimized model did in predicting bupropion outcome. On the held out test data, it achieved RMSE of 4.71 HAM-D points across the outer folds. And for reference, the HAM-D scale ranges from 0 to 52. This model also achieved an R-squared of 0.26, so it explains 26% of the variance in the data, which is quite substantial for these kinds of neuroimaging problems. Another metric we can use to judge our model's performance is number needed to treat, or NNT. This is the number of patients that need to be screened by our model to achieve one additional positive outcome. In this problem, the positive outcome is remission, which is defined clinically as a post-treatment HAM-D less than or equal to 7. So we can take the numerical HAM-D score predictions of our model and threshold them to get a classification prediction of whether each individual will achieve remission. Our NNT for predicting remission is 3.2, meaning that on average, out of every 3 patients we screen with this predicted model, we'll be able to help one additional patient achieve remission, compared to randomly assigning patients to bupropion. This is quite substantial. In psychiatry research, you're typically aiming for NNT less than 10. Finally, we can do some feature importance measurements to find which brain activation measures the model found to be most predictive. And we found that the most important features were located in the medial frontal cortex, amygdala, cingulate cortex, and striatum. This lines up very well with what's known about MDD and its pathophysiology, as these are the regions involved in the dopaminergic reward processing circuit in the brain that's believed to be altered in MDD. To summarize, we combined task-based fMRI, deep learning, and a neural architecture search to build a predictor of an individual outcome after treatment with antidepressant bupropion. This predictor can forecast how much an individual will respond to bupropion, and it can determine if they will achieve remission at an NNT of 3.2. This has the potential to help clinicians determine whether or not to give a patient bupropion, and to reduce the need for tedious trial and error treatment selection. In the future, we hope to explore methods like data augmentation to improve our performance and to extend our approach to other antidepressants and MDD treatments.